Hello, welcome to Autodesk Netfabb Simulation, Lesson 3, Running Part Level Analyses. The objectives of this lesson is to learn how to import a CAD file into Netfabb Simulation and how to select a custom PRM file to pair with that CAD file in order to run a part level analysis. Finally, we will import results for viewing. Just a refresher, analyses in Netfabb Simulation take place at two different scales. The first is a fine scale, which applies a moving source to a small block of material in order to generate a PRM file. The PRM file contains information about how a particular material mechanically responds to a particular machine parameter set. This lesson will focus on the larger scale part of the analysis, where we take that PRM file and pair it with a CAD file in order to get an understanding of how a full part will mechanically respond to these parameter settings. So the first thing we want to do is launch the simulation utility and use the import button to bring in a geometry. There are many supported formats. I'm selecting an STL file. Once you import the part, you can hit OK. My STL file is in millimeters, so I will select millimeters, and it's best to turn colors off. Makes it easier to see the part. So you see I've imported a geometry, and now we're going to go up to the ribbon and we're going to work from left to right. So the first option is to move the part, but it's actually already in the orientation that I want. That was done in Netfabb along with the build preparation. The second option is to size the build plate. You can choose whatever build plate size you'd like, up to the full size of a real build plate, and you can simulate full build plates of parts as well. For this analysis, we'll just do a single part on an arbitrary chunk of material that'll act to conduct energy away from the part. So now we'll go, after plate, we'll go to analysis setup. Right now, the only machine offered is the generic open machine. As time progresses, you'll see this list start to populate with the common additive machines used in industry. And the machine configuration dropdown allows you to select a PRM file. So these are the generic PRM files that are shipped along with the software. There's one PRM file shipped for each material. In this case, we actually want to use a custom PRM file. When we select custom, it's going to allow us to use the process parameter dropdown to access the entire PRM library. In the PRM library, I see Inconel 718 at 150 watts and 40 microns, which is the PRM file that we created in lesson 2 of this tutorial series, and I will select that. Once I've selected that, I will go to the build plate menu, and I'm going to select a steel 304 build plate. I'm going to gloss over some of the more advanced options, and I'm going to cover those in future tutorials. So now we will hit OK, and the next thing we need to do is use the mesh preview button to make sure that we have a suitable mesh for the analysis. So what the solver is going to do here is it's going to interrogate my STL file, and it's going to take a guess at what a reasonable voxel mesh is going to look like. So you see it has fine mesh to capture this detail, but then it knows where it can get away with coarse mesh, like in the build plate. So this mesh captures the geometry that I'm simulating, so it's suitable to solve. So we're going to hit the solve button now. So once we've hit the solve button, what's going to happen is we're going to launch a thermal analysis, where at every time step we're going to calculate the thermal results of the problem and then take those as the initial condition for the next time step. At the end of the thermal analysis, we'll have the temperature of all of the nodes at all of the time steps, and we'll take those temperatures and we're going to input those into a mechanical analysis, which will calculate the distortion during the entire build process. So we can monitor our progress from the job manager. You can see we're already 60% complete with the analysis. And you can use the View Logs button to see what's going on. So this is actually the history of the thermal solve, including all of the time steps in the analysis. And if we scroll down to the bottom, we can see the thermal analysis completed in about 16 seconds. Now we can monitor the mechanical analysis, which looks to be almost complete. And you can see this ran in about 44 seconds. So now it's going to ask me if I would like to import my results for viewing. And I will say yes, I will. And now it's actually imported the results. So in order to see what's going on, we can go to Plot Settings, and we can go to this displacement scale, and we're actually going to warp the results by a factor of 5. That's going to magnify the distortion so you can see better what's happening. And as we click through the results here in the upper left-hand corner, you can actually see as new material comes in, It's hot and expanded, and then it cools and contracts. So you can actually see this pattern happen. And we're viewing the distortion results here. And you can see the distortion actually evolve during the entire build process. So new material comes in, and then it cools and contracts. And then this is the result. So that's the entire workflow from selecting a geometry and a PRM file to viewing results. Just to summarize what we did here, we imported a geometry into Netfabb Simulation, and we paired that with the custom PRM file that we generated as part of Lesson 2 of this tutorial series. We then used that PRM file along with that geometry to perform a part level analysis, and we viewed the distortion results that were calculated during that analysis. In the next lesson, I plan to cover modifying boundary conditions in Netfabb Simulation.